Hello, my name is Pawel Skrzypek. I'm a Chief Technology Officer in the AI Investments, and today with Anna Warno, Senior Data Scientist from 7Bulls, we will make a review of the most advanced and most efficient, at least in our opinion, machine learning time series forecasting methods. I will make a short introduction with slides, and then Anya will make the real hands-on session how to use some of these methods on the real datasets. The brief agenda is as follows. I will tell a little bit more about the time series, what this is, and about the statistical methods which were very extensively used till the 2 years ago, about the M4 and 5 competition. Then I briefly go through the most advanced and effective machine learning time series forecasting methods, and then Anya will show the real hands-on session how to forecast different time series using these presented methods. So for the very long time, the domination of the statistical method was obvious. The machine learning methods achieve much lower results, and the most popular was to use these listed statistical methods. I do not go into the details, but I only want to highlight the fact that the most typical and most popular way of using the statistical method was to ensemble different methods, which is also used very extensively by machine learning methods. The breakthrough was in the 2018 when the results of the M4 competition was announced. M competition is probably the most prestigious scientifically packed competition in time series forecasting. It is organized by the Professor Spiros Makridiakis from the University of Nicosia, and the fourth edition of this competition, called M4, the first and the second place was won by the so-called hybrid methods, so method which uses statistical approaches and machine learning. And machine learning part was, say, much more important for this method comparing to the statistical one. And M4, M5, which results was presented last year, was dominated by the only machine learning methods. As in the M4 competition, the goal was to predict over 100,000 time series, so a very, very big amount of the time series. We consider these results as a very comprehensive and reliable. And the first method is the ES hybrid method by Sławek-Smyl. It is the winning method from M4. It uses statistical approach, exponential smoothing, Holt winters for the data processing, and also use very novel way of the learning the neural network with the special architecture. I will tell a little bit more on the next slide, together with the parameters of the exponential smoothing. This method uses model ensembling very extensively in a very unique and novel way. Another novelty of this method was to use LSTM network, but not a typical LSTM network, but with the dilation and residual connection. Both these concepts are very popular in the image recognition for the convolutional neural network, and this application of that concept was the first one, at least on the big scale, for the LSTM and time series forecasting, and the results was obviously great. So Sławek won the M4 competition, and this architecture was very heavily studied by other scientists and person working on the time series forecasting. One more very important thing about the ES hybrid method is that it uses the ensembling in a very advanced way. Yeah? So the models, the best models for the given time series, please remember that it was used for the 100,000 time series, was collected, and as for the final prediction, that these models were used to achieve the most robust and accurate results. The second method, which is purely machine learning method, is NBITS. It was published after the M4 competition and claims to get the better results on the M4 data sets comparing to ES hybrid. This is purely machine learning method. It has a unique stack block-based architecture, has different type of the block, trend, seasonal, generic, and also have some explainability and transfer learning features, and as well uses advanced model ensembling on a very big scale. It ensembles over 100 models to make a prediction. This is the architecture of that NBITS method, and as you can see, there are many stacks. Each stack is built of the block, and also there are these residual connections within the stack. So the input from the one layer is passed to the given layer and also skip this layer to go to the next layer. Very unique concept is also to push the results of each block, and combine them together and use them as the output from the stack, and each stack is adding their output to the global forecasting, which is ensembled inside the given model. So the NBITS heavily rely on the ensembling in a very good way, and is the fully pure machine learning method. The next method which I wanted to mention is the complete framework called Gluon TS. It is the complete framework for the time series forecasting. It includes various models, also the most advanced neural networks architecture like transformer, and different method of data transformation. Also it allows for the probabilistic time series modeling to determine the distribution. It supports for the cloud computing, training and inference, and also has a very strong community support. And as I said, this framework is ready to use. So you can download that library and start using. It's not easy to use, but it is easier to use than previous two methods, which are available only as a source code, and you need to download and compile it by yourselves and start using. Here you can see I'm not sure if it's the latest diagram, but it shows that how many components is already included in the Gluon TS, and the framework is still developed and used for the time series forecasting. The next method which I wanted to mention is Tsetlin machine. It is based on the stochastic learning automata invented by the Russian scientist Tsetlin in the 60s of the previous century, so quite old. But for the long time this algorithm was used only for the scientific purposes, but now it's used for the both machine learning and also for the reinforcement learning, so for supervised learning and reinforcement learning. And from my point of view, the biggest innovation of this approach is that it allows to create or to learn the stochastic distribution for each of the parameters. So this algorithm is learning the probabilistic distributions, which is learned in the supervised way, and also is constantly updated after each prediction. So that's the reason that this approach is considered as a self-learning, and can be used for the reinforcement learning and also for prediction. And the advantage is that we do not need to retrain a model after each prediction, but this model is somehow retrained after each prediction, so the weights of the probabilistic distribution are changed after each prediction. And very briefly, it works that way that we have the input, and for each parameter of the input, the separate stochastic distribution is created, and based on the rules in this Tsetlin machine, the probabilistic distribution is updated. And for the prediction, the final prediction for the final value for the output of each parameter is sampled for the currently learned distribution, and finally it is ensembled in the given way. This Tsetlin machine is a very different approach comparing to the, let's say, traditional machine learning, which is based on the neural networks usually, and stochastic gradient descent and backpropagation process, because it's learned in the different way, and it could be used as the one additional method, for example, to be included in the ensembles. Anya in hands-on session will present the traditional machine learning method, so yes, hybrid and NBITS, and one more method called temporal fusion transformer, which is considered as one of the most advanced currently available machine learning methods, and also Anya will introduce these methods, so I will skip this temporal fusion transformer for now. So that's all about reviewing the methods. Very short summary, the highlights of the forecasting. From my point of view, the most important thing is that currently the time series forecasting method, machine learning based, are very dynamically developed, and the new methods appears. They are not, let's say, typical convolutional LSTM or transformer methods, but much more advanced. And the efficiency is much higher in terms of the prediction accuracy, is much higher than statistical methods. Of course, forecasting methods has many areas of application in the AI investments. We are using them for the financial time series, and we achieve over 60% accuracy on the long 10 years test periods. But of course, the application of the time series forecasting can be used for the many different areas, like business, sales, retail, and also for social purposes like health, environment, and mobility, and many more. So having the more accurate method gives a significant edge in many areas. So that's the reason that we are presenting it here. Okay, now it's time for the hands-on session by Anya. As I said, Anya will show the NBITS method, TFD method, and also some basic introduction how to properly forecast time series using machine learning approaches. I hope you find our sessions valuable and can learn something interesting from that. So that's all from my side, and now it's time for Anya and hands-on session.
Hello. After the theoretical introduction, I would like to show something practical. I would like to present how we struggle with time series data on a daily basis. I will talk shortly about the data processing, models choice, models evaluation, boosting accuracy, and explainable AI, which can be used with time series data. And to have some examples, I chose a publicly available dataset. The selection criteria were multidimensionality, difficulty, and data size. And I will briefly show what can be done with such data. So, as I mentioned before, these data are open sourced. There is around 40,000 of rows each for one timestamp. Frequency of the data is 1 hour. And we have around 15 columns, 6 main air pollutants, 6 connected with weather, and the rest express the date. Here we have some example columns plotted. As we can see, data look messy. We have large amplitudes. After zooming data plot, it looks slightly better. However, there is no visible pattern at the first sight. Only after aggregation, example over a week, you can see some regularities. And normally now we would do some explanatory data analysis, etc. However, we don't have as much time, so we will focus only on parts which are absolutely necessary, which are crucial for modeling. So one of the first things which needs to be done is handling the missing data. Firstly, we need to understand the source of missingness. Does it occur regularly? What are the largest gaps between consecutive not-nonce values? Here I have plotted some missing data statistics. Starting from basic bar plot, as you can see, many columns do not contain any nonce, but there exist columns with significant amount of missing values, such as carbon monoxide. Next, heat map. Heat map helps us determine which occurrences of nonce in different columns are correlated. We can see a strong correlation of columns describing the weather, such as pressure or temperature. Correlation of occurrences of missing values in different columns might be also expressed with dendrogram here. And apart from basic statistics and correlations, we can check the distribution for specific columns. We can select column, and here we have length of consecutive nonce histogram. As we can see in this example, most of consecutive nonce sequences are short. However, series as long as 60 also exist. And the red plot shows the length of gaps between missing values. So, if it was a straight line, that would mean that non-missing values occur regularly. They do not in this case. So now we need to handle the missing data. We could apply standard basic methods like backward filling, linear or polynomial interpolation. We could also use more advanced methods, for example, based on machine learning models. Here we have example. In the plot we can see fragment of one of time series. For visualization purposes, we can artificially increase number of missingness. We can select the percentage of values which will be randomly removed and see how different simple imputation methods will fill these values. So, starting from forward filling, through linear interpolation, to spline with the higher order, which will give us smoother curve. From analysis of missing values, we know that in our case, sometimes the gap between two not missing values is very large. Here we have plotted example. We will not insert anything in that case, but just split series into two shorter series. Second thing which needs to be done are data transformations. This step is crucial for some statistical models which require often series in specific format, for example stationary. For more advanced models, it's often not essential, but may also help with numerical issues. Here we have listed some basic transformations which can be applied for time series, and we can see how our series would look after the given transformation. We can also use more advanced transformations like embeddings. Example of simple but effective time transformation is encoding cyclical features like hours, days, etc. into a unit circle, like in the presented GIF. And for that we are using this formula. So before the modeling for our task, we will fill missing values with linear interpolation, normalize features. Sometimes we use also box-Cox transformation and encode cyclical features into a unit circle. In our case, hours and days. And for modeling, we choose one column, nitrogen dioxide, and prediction horizon equal to 6. And first we will train baselines and simpler statistical models to have some point of reference, and then we will move to neural networks methods. And before the models results, a few words about the training setup. We'll use train, validation, and test split. And for evaluation, we'll use rolling window. Here we have plotted train, validation, test splits. And we will start with extremely simple models, naive predictors. It's good to always look at them in time series forecasting. They are very, very easy to use, and it often happens that the metrics, graphs, results, statistics of our model look okay at the first glance, but then it turns out that the naive prediction is better and our model is worthless. So it's always it's a good practice to start first with naive prediction. And it's worth to mention that some alternatives for naive predictors would be usage of metrics like mean absolute scaled error. And apart from baby baselines, we will also train some classical models, for example, Sarima, Prophet, Tibet, or exponential time series smoothing. And these models will be fine-tuned with rolling window, with hyperparameters grid search or Bayesian-based hyperparameter search. Okay, so as we have seasonal data, we'll use two naive predictors: last value repetition and repetition of values from the previous day with the same hour. And here are the results. We'll compare them later with other methods. And for advanced neural networks models, we'll choose two methods: temporal fusion transformer and NBits. Both of them are the state-of-the-art models, and they have different advantages and complete each other very well. In this picture, we can see architecture of temporal fusion transformer, and as you can see, it's quite complicated. But we will not talk about the technical details. We will focus on advantages of this model. So first of all, good results according to the paper, comparing to statistical and neural network models. The very, very big advantage of temporal fusion transformers is the fact that it works with multivariate time series with different types of data, like categorical, continuous, or static. Temporal fusion transformer has also implemented variable selection network, so it allows us save time during the data preprocessing. Its results are interpretable thanks to attention mechanism. It also works with known feature inputs, and that allows us creating conditional predictions. In general, it's applicable without modification to a wide range of problems, and we could obtain some explainable predictions. And the second chosen model was NBits, and NBits outperformed the winner model from prestigious and for competition. It means that it achieved the highest scores on 100,000 time series from different domains. So it's a badge of quality. It's designed for univariate time series. Its results are also interpretable, but thanks to special models which try to explain the trend and seasonality. And to sum up, TFT and NBits both have very good scores and try to deliver interpretable predictions, but are optimized for different types of data. NBIT is optimized for univariate time series, and TFT is optimized for any type of time series with any type of data. With any types of data. Okay, so for neural network training, we use early stopping, learning rate scheduler, and gradient clipping. And sometimes, but not in this case, we use also Bayesian-based framework like Optuna for hyperparameters and networks architecture optimization. Okay, so let's move to results. The accurate metrics results will be presented later in the table, but here we have some GIF for NBIT performance on the test set. And this gray rectangle represents the prediction horizon, so its width is equal to 6, because our horizon is equal to 6 hours. And the same GIF was delivered for TFT. And data are noisy, but predictions sometimes look okay. Model often correctly predicts future forecast direction, which is good. And here are some predictions for TFT from test set, which are actually very good. And they were selected randomly, but luckily we ran very good samples. For sure, there are also worse examples in this test set. And here we have table with different experiments with TFT and NBIT and different loss functions. Different loss functions for regression problem. And here we have also metrics results, like typical metrics for regressions, like mean absolute error or mean average percentage error, etc. And the best scores are highlighted in green. And as we can see, temporal fusion transformer with quantile loss scored the best. Mean average error for naive prediction for naive predictors were around 25, so our neural networks clearly learn anything and are significantly better than naive predictions. And the next question is, can we do better? Of course, we can try to optimize hyperparameters or network architecture, but there is one thing which requires less time and is extremely effective: ensembling. Even models with the same architecture, trained with different loss function, input length, training hyperparameters, or transformation can contribute to score improvement in assembling. And here we have a proof. These are experiments with TFT or NBITs and differing only in loss function. So, for example, we used quantile loss, or mean absolute error loss, or root mean square error loss, or new loss function, delayed loss, which is different than which is significantly different than this other losses. And we end up with over 15% of mean absolute error improvement over the best single model. And even single models with low score, like this one, TFT with delayed loss, the worst model from all experiments with TFT, contributes positively to score improvement. And as I mentioned, both TFT and NBITs aim to give explainable predictions, and here we have results obtained from TFT. First plot shows the value's importance in time. So the higher is the value here, the more important was that time point during the predictions. In this case, the most influential data were measured 168 hours, so 7 days before the prediction time. So it means that it suggests that we can have weak seasonality here. And here we have features importance from variable selection submodule. As expected, the most important feature is nitrogen dioxide, so our target. And decoded variable importance plot for feature known values like those connected with time. So it shows which features were the most important from the known feature inputs. With small modification of architecture, we can also see which features were the most important for specific timestamp. As I mentioned, to obtain such result, we need to slightly change architecture, so there is no guarantee that model will work as good as the original one on any type of data, but for some examples it also works. It relies on the same mechanism like the original TFT, so it uses attention layer for explainability. Okay, and that's all. Thank you all for attention.